Next, we're going to look at a spread. Now, this is kind of kind of a weird one. It's really interesting though. So a spread is an extension of a cohesive soil or rock mass combined with the general subsidence of the fractured mass of cohesive material into softer underlying material. Okay, what does that mean? It's sort of what it sounds like. It spreads out, but then sort of sinks down. Obviously, like if you stretch it out, it's got to get thinner as it goes, right? Um, yeah, so the most common one of these is what's called a lateral spread. So a lateral spread usually occurs on really gentle slopes, or it can even be completely flat, which is sort of interesting. So what happens is you have an upper layer of rock that's a lot stronger, it's a lot harder. And below it, you have a softer, weaker layer. And so a lot of times, what happens here is the weaker layer that's on the bottom is actually flowing because of liquefaction. So we've talked about liquefaction in the past because we talked about it in terms of earthquakes. So you have some sort of like weak layer under there that's prone to liquefaction, and there's an earthquake. And so that layer starts kind of flowing. This also could happen because of saturation of that weak layer. It just gets way too wet. And that could be due to rainfall, snow melt, or just groundwater changes. Let's say you dam a river and the reservoir is filling up, and now it's able to your groundwater table rises quite a bit up into a softer layer. It can also happen for marine clays if there's some sort of disturbance at the base of the slope. And that could just be wave action, which I will show you. There's a couple of really big examples of it. Now this one, it's a little strange, but this is actually due to liquefaction too, along the Amazon River. So the river actually deposits lots of clay material. And if it gets shaken, everything starts spreading. Now it's not a sinkhole. It is just a lateral spread, but let's see if I can get this to play for us. Now, some of the parts of the video are real time. In this case, is from a security camera, and it's sped up, but you can see like everything, there is a layer of clay that's flowing out towards the Amazon River and out into the water, and you can sort of get a feel for where that failure plane is when they show us the scarp here. The Amazon, unfortunately, this is a port along the Amazon that is really important for shipping. And so, ocean liners come in to the Amazon and drop off the really big shipping containers, and then they're picked up by trucks or railway and carry them further in or out. But I sort of love watching this and watching it rip these in half. There's one I love watching fall in. Oh, is this him? No. We'll keep an eye out for it. Oh, there you go. No, I'm laughing. This is actually pretty tragic in terms of, for one, pollution within the river right now, because there is no telling what is in the shipping containers. But for two, like just the loss of all this material, because, this could be food, this could be dry goods, it could be shoes being sent over, it could be electronics, it could be important medical equipment. So it could be any number of things that have spilled out there, but what a mess. In this case, what they think it was probably caused by was they were doing some road work on the road that goes up to this port area, and so just the shaking from the road work and from all the equipment could have actually set this off, which is pretty wild. So these can move really slow. They can also move fairly rapidly, but it depends on the triggering mechanism. Here's another example that happened during an earthquake, and we actually talked about this earlier in class. The Turnagain Heights landslide. This happened during the Good Friday earthquake of 1964. This was the largest earthquake to ever affect the United States and the second largest one ever recorded. And during the earthquake, it was a 9.2, so it shook these layers of silt and clay. It's called the bootlegger clay that was down below here. And the bottom picture shows you just how spread out everything got. There were actually some places of the original bluff on the shoreline that actually moved as much as 2,000 feet out into the bay. That's like it's less than half a mile, but maybe 2/5. I mean, it's a pretty good distance, though. Unfortunately, though, there was a big housing development known as the Turnagain Heights subdivision right on the bluff. It was nice views there for a while, and it ended up destroying 75 houses. And you can see some of those here, but this is sort of what it looked like when everything finally came to a stop. So that hard kind of upper layer of soil of rock stayed fairly cohesive, but as it was moving, the blocks were turning and sliding and part of them sinking down into those clays, which is what you get here. So you can see the house in the background is sort of tilted off to our left, and the tree that's right between us and the house is leaning over like at a 45-degree angle. These images are quite a bit of mess. Here's a shot from above, kind of looking down at that landslide mass. But you can see there is subsidence of the material because it's sinking down as it's moving and spreading out. Now, they happen worldwide, at least where you have liquefiable soils, right? About the only thing you can do here is just avoid building in areas where you have this soil that can liquefy easily, especially in earthquake prone areas, but sometimes it's sort of hard to avoid. Now we're going to look at flows next. This is actually one of my favorite types of movements here, just because it's pretty closely related to some of the stuff I was doing in grad school. So a flow is displacing material in a way that resembles a viscous liquid. So if you remember from volcanoes, viscosity is the resistance to flow. And so something that's viscous is fairly thick. So it looks like a big, thick fluid. Although I'll be honest, some of these move so fast that you don't really see a change of, it doesn't really look that particularly viscous. Now, often you get a gradation of change from a slide to a flow. A lot of times because of the water content or just how the movement changes. So you'll start with like a landslide or a rock slide or a slump, and the bottom of the toe of it'll change into a flow. And we saw that pretty obviously in the Oso landslide. All right, so a debris flow is a form of rapid mass movement in which loose soil, rock, and sometimes organic matter combine with water to form a slurry that flows down slope. You may also hear the term mudslide just because of the really fine stuff. So a lot of times if the stuff moving is pretty small, it's referred to as a mudslide or a mud flow. And if it's really big rocks, which sometimes it can be, we usually use the term debris flow, more likely. You can actually get dry flows as well. Sand in particular tends to act as a fluid, even though there's not a lot of water in there or even any at all. Now, these things are particularly deadly because they do move so fast. They can also move fairly slow as well, but they do move pretty fast in some cases. But they're often in steep gullies or sort of confined into canyons. So one of the big things is not being in canyons during heavy rainfall where you are, or upstream, or in particular building along canyons. And in California, Southern California in particular, you see a lot of homes and housing developments built down at the mouth of canyons that are pretty scary. So here's one of my beautiful examples. This is La Conchita, California. And they had a flow or a slump, a little bit of both motion, in 1995. The good news was this moved pretty slowly. and everybody was able to evacuate. And you can see down at the bottom, there were a number of homes that were covered up, but not very many. Except in 2005, there was a reactivation of that. And if you look in the image here, you can see on the bottom right, it's covering a lot more area now. There's an entire city block that's basically covered. This one moved a whole lot faster, and it moved as a debris flow. I think, oh, I did. Yay. Somebody actually caught this happening on video. So this is that debris flow coming down from the slopes above. So unfortunately, what happens is when it moves this fast, there's not a lot of time to evacuate or to get out. And unfortunately, what that meant for the town of La Conchita was that they ended up having 11 deaths. And this is not a big community. This is literally the entire thing. And what you can't really see from here is this is sort of the northernmost road at the very bottom of the image. There is one road into town, and it is on the bottom right, sort of just below where the landslide mass is. There was a single road into town, then there is railroad tracks, then Highway 101, and then the ocean. Which is why somebody was filming it that already had mudslides like north and south of this area over the 101. And so they were filming those. But this was catastrophic for this area and quite heartbreaking, honestly. And what's happened is they've just left the landslide mass there at the bottom of the slope and all the homes still buried. They got to what victims and survivors they could, but then they've left it alone because to move any of that would unstabilize the whole thing and likely lead to another landslide. But if you look at this image, though, it's sort of obvious this is not the only one. So if you look across it, you can see a bit of like a dirt road up the slope behind, just north of town. There's a lot of little bitty slides through there, but there's a few big landslide scars as well along the way. At the very top of the cliff there is actually an avocado orchard. And they were partially blamed for this particular landslide because avocados need a lot of water and they tend to overwater it. And between that, the irrigation and heavy rainfall they had, it created an increase in groundwater and a pretty saturated slope there. This is another one. This is literally one of my favorite videos ever. So this was taken in the Andes Mountains right on the Argentina-Chile border. This is a guide company that takes a bunch of people out and hikes them through the Andes if that's what they're into. Gonna get it planned. Uh-oh, it's not starting where I wanted it to. Gonna go down. All right, you can see they're crossing this little gully. I'm going to turn the sound on for you because it's much more dramatic that way. And they're kind of checking upstream. There's a little bit of water. You hear it coming. This is real time too. Like nothing is sped up here. I'm always horrified when that hits. For one, they had really good guides that got them all moved quickly. But if you look at the ground around it, the whole area they're walking on was created by these debris flows. Slowing down a little bit, but you're going to see there's another pulse here in a second. But notice the size of the rocks being carried by this thing. These are huge boulders. Now, if this was just water, it couldn't carry those boulders. The mud mixed in makes it a lot more dense, which means it can actually float those boulders. So the density and the speed of this is why some of those boulders are floating. So in this case, you can have really thin and really watery, really fast moving stuff. You can have really thick debris flows with lots of sediment and debris in it that moves a lot slower. A lot of times it's just within gullies or canyon or valley areas, which is what you see here. The water's splashing up pretty high. You can see what's getting wet. But the good news for these folks are the material is mostly staying within there, so they're safe being up and out of the way. These happen in particular particularly where you've had loss of vegetation, and that could be due to either wildfires or logging. They're really common in volcanic areas, and we're going to look at lahars here in a second. They can move really fast. They can move really slow. I think I already saw that one. And it's often due to intense surface flow water, so really heavy precipitations really fast. Debris flows are a big problem throughout southern Arizona because our water, when it rains, it doesn't infiltrate very well because we're such an arid region. And when we get rain, it comes down really, really fast. Most of what can be done here is putting up warning systems, and that's one of the things that's happened in La Conchita, is they have warning systems, but the best part is just to not be in these areas at the mouth of canyons that are prone to debris floods. Here's another example from Montecito, California. So they had fires during the winter of 2017, 2018, and then they had just a massive series of rainstorms. It might have been one of the Pineapple Express storms, but it just dumped water on them like crazy. And soils that have been in a wildfire, soils that have been burned, are what we call hydrophobic, which means they actually repel water, so that you have these slopes with basically no vegetation on them, and the soil refuses to take in any of the water, so it slides over the top of the surface really easily. We call this surface flow or sheet flow. And because Montecito is down towards the mouth of some canyons or some mountains, they get to going really, really fast, and they carry some big old boulders. And you can see this house has been just buried. Unfortunately, this also led to quite a few people being killed. I found the number of about 20 that were killed during these debris flow events. This one's pretty similar to the one in the Andes, but here's UA debris flow up in the Himalayas. Look at the size of that rock. And it's like floating, y'all. Holy crap. But you can see just how big of stuff ends up getting brought down with it. I'm looking at the time thinking I need to move on, but I really just want to watch this video for a little bit. Watch these huge ass boulders moving. So yeah, really scary stuff. And these folks, but because it stays within that little valley, and you can see it's not uncommon to have these going down this particular valley. They're fairly safe. So I mentioned volcanoes earlier. There is a special type of lahar, or a special type of debris flow called a lahar. In this case, lahar is actually from Indonesia, and there's a lot of volcanoes there, which totally makes sense. These are also called volcanic mud flows. So lahars are flows that originate on the slopes of volcanoes. It mobilizes ash or weathered volcanic rocks that make up the slopes. And these happen on pretty much all volcanoes, pretty much anywhere all over the world. This can be a result of a volcanic eruption, or it can be just because of snowmelt or flooding on a volcano that mobilizes that stuff that's already there. Lahars often result in large number of casualties because, as you saw with the debris flows, they move pretty fast. And when these happen on stratovolcanoes with really steep slopes, they get to moving very, very quickly. And in the case of an eruption that melts a lot of snow or ice very quickly, you may not have just a whole lot of warning. This particular image is showing you Mount St. Helens. This is after the 1980 eruption because the hole is already blown out and there's snow in it. So I know this is a little bit later. But stratovolcanoes in particular kind of is what I happen to think of with lahars. Because they're very tall and they're very pointy and they have snow on them quite often. Mount St. Helens actually had glaciers on top of it prior to the 1980 eruption. And so when it erupted, you ended up with lots and lots of lahars. Got a couple of views of lahars for you, and I know we talked about these and covered these fairly well when we did volcanoes, but I thought it's worthy of mentioning just in the terms of debris flows. You can see here. Now these can happen from crater lakes being drained. They can happen from condensation of steam being erupted, or it can melt snow and ice at the top of the volcano. Sometimes it's just rain falling on top. For instance, Mount Rainier has a big lahar problem, and it's not currently erupting, but they still have lahars. Some of the largest and most deadly lahars have originated from eruptions or venting, which suddenly melts the snow and ice. It causes liquefaction and catastrophic speeds as it moves down the slopes of the volcano. And there's really not a lot you can do in terms of lahars. In some cases in Japan, they have created viaducts to kind of funnel the lahars down in areas they know it. But basically, the most important thing is just not building on volcanic slopes or at the bottom of some of those really big gullies or canyons coming down from them. Probably the most famous lahar in history was the lahar during the eruption of Nevado del Ruiz in 1985. And this is a little video. This is more recent, but you can see the little GIF of Nevado del Ruiz with a lot of steam coming off of it. But my understanding is the name of the volcano even references the amount of snow that's on it. And so when it erupted in 1985 and melted all that snow, it came down in a huge lahar that pretty much wiped out the whole town here in Colombia. And we talked about Omaira Sanchez. This is a little bit different view of her down in the bottom right, though. You can see how desperately people are working and trying to get her out, which unfortunately didn't work. But in this case, I wanted to show you sort of a lot of the people in that lahar deposit and kind of stuck in the mud. Just to kind of give you an idea of kind of how bleak it looked. And unfortunately, somewhere around 23,000 people were killed because of this lahar. Now, something else that happens on volcanoes is a debris avalanche. So this is a really big type of debris flow. So the biggest difference here is the scale of it. So this is a large, extremely rapid, often open slope flows, which formed when an unstable slope collapses. And the fragmented debris rapidly flows down the side of the slope. They occur worldwide, but they're kind of most common on really steep volcanoes. They can follow drainage courses or even just take out the whole side of the volcano. Some large debris avalanches have been known to pick up blocks as wide as 3 kilometers wide and move them several kilometers from when they started. So this is apparently a pretty famous one in Tanzania. That's where Kilimanjaro is. Sorry, I'm doing that off the top of my head. But you can see these kind of the outline of the deposit here is really, really big and kind of only stopped moving because of the slopes of Kilimanjaro. Here's a view of Mount Shasta, and if you ever drive through, you may not notice it too much, but you can see Shasta in the distance. But these hummocks, these little hills in the front, those are from a debris avalanche off of Mount Shasta. And you can see they're pretty darn far away. And these go from being rapid to very rapid. Some of the debris avalanches can travel at close to 100 meters per second, which may or may not mean anything to you. I looked it up. That is over 200 miles an hour. So when we talked about volcanic hazards, we talked about pyroclastic flows, but these debris avalanches move just as fast, although not as hot, which is pretty scary. Which again, that speed makes them particularly deadly. Now there's kind of described as two types. One is a cold debris avalanche, and this is just from an unstable slope. You're looking at sort of just weathered material and really steep terrain. It kind of slides down those steep slopes. But a hot one results from volcanic activity. And it could be a volcanic earthquake or injection of magma, which can increase slope instability. There you go. This shows you sort of how the Mount Shasta formed, the area that was lost and all the hummocks out here. But, of course, we can't talk about giant landslides on volcanoes without mentioning Mount St. Helens. When Mount St. Helens erupted in 1980, the sequence began when magma was infilling into the volcano magma chamber, and it created a big old bulge on the north side of the volcano. And on the day of the eruption, there was a pretty strong earthquake. And that earthquake actually ended up dislodging that bulge, and the bulge, along with about a third of the mountain, slid down. And that's what started the volcanic eruption. And this is further shots from it there. So once everything slid down, then it reduced pressure on the magma chamber and opened it up to start erupting. The other one that's pretty awesome, that's worthy of mentioning, is Hawaii. Now, we tend to think of the Hawaii as like separate islands, but if you sort of take away all the water, there's actually a big long ridge with little mountains dotting it. So it's a mountain chain, basically. But if we look at the underwater topography, these are actually outlines of landslides off of the Hawaiian Islands. And you can see sort of some of these are pretty big, and you can actually see the debris from the avalanche or the rock avalanche going out. One of the largest ones, though, is over here off of Oahu. So this is the Nu'uanu landslide. This is enormous. The biggest block, which you can sort of see under the SLI there, where it says landslide, the largest block is 19 miles long and 11 miles wide. That is an enormous block, and you can see just how far these were able to move. And apparently it took out about a third of the island of Oahu, failed during this particular debris avalanche, which is really scary. But obviously, if you have that big of a landslide out to the ocean, even worse things happen. So this actually generated a really big tsunami. Now, the tsunami was able to reach most of the Hawaiian Islands within half an hour from this time the slide started. There was a wave over 100 meters tall on the northern coast of Oahu and Molokai. And the southern coast, it was 20 to 30 meters high. It finally reached the west coast of North America about 5 hours after the landslide started. It reaches Japan in 8 hours. But if you look at how it's all kind of set up, it was actually strongly directed towards South California. Yeah, LA, San Diego, that whole area. The tsunami heights in those areas were probably as high as 70 meters high because of this landslide. Now, here's the good news. It's been a while. It happened somewhere between 500,000 and 1.5 million years ago. So it's been a little while, but those are still out there. And if they've happened before, they will likely happen again, which is terribly scary. And of course, we couldn't forget tsunamis triggered by landslides if I didn't mention Lituya Bay in 1958. There was an earthquake that dislodged a glacier and rock into the waters of Lituya Bay to make one of the largest waves ever recorded on Earth. All right, now, less dramatic. Sorry, we have earth flows. So earth flows occur on general to moderate slopes, and usually where you have fairly fine-grained soil like clay or silt. But it could also be just really weathered rock because that has a lot of clay in it as well. So the mass in an earth flow moves as a plastic or viscous fluid but with strong internal deformation. So it's moving and folding and rolling inside there. So in particular, quick clay is really vulnerable. If you remember that video from the Amazon River, and that can cause damage in really big areas because of that. And these pretty much happen worldwide. They go from fairly slow to pretty rapid, which is a pretty big is a pretty wide range here. They're used, the common triggers that actually cause these are saturated soil, again, rainfall or snowmelt, a lowering of water surfaces, you have a rapid drawdown on the groundwater table, or a stream, or excavation, or excess loading, or earthquakes. There's a lot of things that can happen. So this is one that happened in Russia. There's not just a whole lot of information about it. I've actually got 2 different locations that I found of where this happened. It was just a video that got posted on social media. But you can see this is actually a pretty awesome video if you watch the whole thing, because all of this is just flowing. And this is likely due, you notice all that snow. This is likely due to snow melt and possibly permafrost. This is another pretty famous earth flow that happened in the Snake River Canyon up near Jackson, Wyoming. They had, of course, heavy snow melt and rainfall, and some steeper slopes thanks to road cuts, but you also have a river that can cause some problems too. At its height, this actually moved at about 50 centimeters per hour, which isn't just a whole lot, but I love this little time-lapse video. So that is that earth flow from above. Taken by the Department of Transportation. What I really liked, though, was when the people show up and it goes all Charlie Chaplin-y. Where'd they go? Where'd they go? Where'd they go? Come on. Oh, here he goes. But you can see he's just like standing and chilling there. This is sped up. I forget by how much, but it's quite a bit. So he may have noticed it was sort of moving slowly. He may not have, but it's pretty awesome one way or the other. All right, one last type of flow here for you. This is creep. Now, creep is an informal name for a really slow earth flow. And the key here is it's imperceptibly slow, and everything just kind of moves downhill. You don't need any particular trigger. All you need is a slope, and it can be a really gentle slope too. But everything just sort of slowly rolls down the hill. It's widespread around the world. It's the most common type of landslide. And it can happen before kind of big, more rapid landslides. It could be sort of a sign that things are going bad early on. In permafrost areas, we have something called solifluction, which is a type of slow creep too, where you have things that are starting to melt, that kind of or that thaw out, kind of oozing down the permafrost layer. These are usually really, really slow. You're looking sometimes less than a meter a decade. A meter. That's not very much. So it goes pretty darn slowly. But it's just kind of, water over time is what does it. It's actually pretty hard to recognize sometimes because it moves so slowly. And if it's an area that's had fairly recent, clearing done to it, you may not even see some of the signs of it. What's interesting is it is really, really slow and sometimes hard to see, but it's the most expensive because it basically never stops. And these are kind of fun. One of the big recent ways you can recognize creep happening are things kind of falling over, fence lines that are sort of crooked and tilted. But I love the curved tree trunks because trees grow straight up towards the light, but if they're sliding down the hill, they sort of curve slowly over time, just sort of get to stay pointing straight up, which is pretty wild.